So the last video of Unit 2 is dealing with calculating the enthalpy of a reaction experimentally. So the technique that we're going to use is called calorimetry, and it is really just the experimental method for determining heat flow at constant pressure using a device called a calorimeter. Now, how are we going to do that? We're going to do it by measuring the heat change of the surroundings and using that, inferring what's happening with the system. So keep in mind the energy change that we measure is the surroundings. And then we have to use this idea that the energy change of the system is equal but opposite. Now, negative does not mean negative energy. Negative means opposite. So if energy is lost by the surroundings, it's being gained by the system. Because remember, conservation of energy, no energy is lost or gained. All right, so in order to do that, we have to apply a heat constant called heat capacity or specific heat capacity. In all three cases, it is simply the amount of energy required to change a substance by 1 degree. Heat capacity doesn't specify quantity of material. Specific heat capacity uses 1 gram of material, and then molar heat capacity is the expression of 1 mole of material. And you can see some heat capacities of various substances here in this table. The idea of heat capacity, how do we figure out the energy? We're going to use heat capacity with this equation. This one hopefully looks familiar to you from first year. Q equals mc delta T, where m is the mass of the material, c is the specific heat of the material, and delta T is the temp change. So this becomes important because this is the equation we're going to use to measure how the energy of the surroundings is changing. The system could be a little bit different, but this is the energy change of the surroundings. So a couple different situations. So if all we're doing is some sort of physical change, like increasing the temperature of a material or decreasing the temperature of a material, the equation that you're going to use, again, starting with Q system equals Q surroundings, is going to get modified into this version. mc delta T equals mc delta T. So the mass times the specific heat times the temp change of the system, in this case, a chunk of iron that's starting at 500 degrees, dropping down to 32.5 degrees. And its specific heat is what we're trying to find. That's going to be equal to the 100 grams of water that changes by this temperature and has this specific heat. So when all you're doing is changing the temperature of materials, both sides of the equation can be mc delta T. Important thing, final temp in a situation like this is always going to be the same for both the system and the surroundings. If the temperature of those two were not the same, you would still have energy exchange going on. Energy always flows from high energy to low energy. So you'd still have energy exchange going on. But once the energy exchange is complete, everything's at the same temperature, then you can use the information to measure or to calculate the specific heat of your sample. All right, so rearranging this equation to figuring out the specific heat of the iron, I plug in all my numbers that I have, and I wind up getting a value that is expressed in the units of joules per gram degree Celsius. How much energy does it take to change the temperature of 1 gram of material 1 degree Celsius? That's the idea of specific heat. All right, so moving on to take a look at chemical reactions. So not just changing the temperature of something, but actually breaking bonds and rearranging atoms and so on and so forth. We are going to take a look at a couple different ways of doing that. In the lab, what we have always used is the constant pressure calorimeter, coffee cup calorimeter. So pretty primitive. You've got a water sample in here. The chemical is going to cause the temperature of this water to change, and we're going to read the temp change of the water. So still dealing with this idea, Q system equals Q surroundings. The system, obviously, is the chemical reaction. The water is going to represent our surroundings, and hopefully you realize that's a little bit of a misinterpretation because not all the energy from the system is going into just the water. It's going to go into the cup and the thermometer and the stirring wire. So this is a big assumption that we make, which is why our experimental yield is never as good as our theoretical yield, because not all the energy actually goes into the water. It goes other places as well. All right, so Q of the water is equal to MC delta T because all we're doing is changing its temperature. Q of the reaction is M delta H, the specific heat of the reaction, it's the specific heat, the enthalpy of the reaction times the mass of material. So we're going to set those two things equal to each other. And typically you want to know what the enthalpy of reaction is, so you're going to divide the Q of the surroundings by the mass of your material. So again, this should look reasonably familiar to you. So example, we're going to dissolve sodium chloride in water. We want to know what the specific heat of solution for that sodium chloride is. Q system is equal to Q surroundings. In this case, the surroundings, now here's where you got to be careful. The surroundings is actually the solution. Solution is not just water, but it's also the salt. So the mass of the solution is actually the total mass of the water and the salt combined. The system is just the salt, so there's nothing hokey about that side. So when you solve this problem, the mass of the solution is everything together, but then we divide by just the mass of the salt. Typically, a delta H is going to want to be in kilojoules per mole, so we've got to take that joules per gram, do some converting in order to get to kilojoules per mole. So keep this idea in mind. It's important, and I'm going to reiterate it. If the chemical is actually in the water, so you have a solution, the mass of the chemical has to be added to the mass of the water when you're figuring out what the mass of the surroundings actually is. If the chemical is kept separate from the water, for example, when we did the food burning lab last year, the food was below the can with the water in it. You don't have to add the mass of the food in that case. So if the chemical is actually in the water, you got to do M solution. If the chemical is not in the water, it's just M water. A more sophisticated way of calculating enthalpy, especially for combustion reactions, is using something called a bomb calorimeter. Bomb calorimeter has a small chamber in which the reaction is going to take place. Oops, click the button. So you're going to burn the sample in this chamber. We're going to make sure that there's plenty of oxygen coming in. We've got an ignition wire, but otherwise this thing is contained. So when this thing burns, the energy is going to be absorbed by only two things. It's going to be absorbed by the bomb, and it's going to be absorbed by the water that surrounds the bomb. And these other chambers are so insulated that no energy is getting out. So we've got to do some of the calculating a little bit differently. Because this is such an efficient device, we actually can figure out what the specific heat of the calorimeter is. And so to figure out the energy of the reaction, if you know the specific heat of the calorimeter, it's really easy to do. But you've got to figure out the specific heat of the calorimeter first. So to do that, you've got to use a material that you know the enthalpy of. So the idea uses this equation to start with. So if you don't know the specific heat of the calorimeter, you've got to figure out how much energy is actually going into the calorimeter versus how much energy was going into the water, because the total energy coming from the reaction should be the sum of those two. Once you know the Q of the calorimeter, you can use that to figure out the specific heat of the calorimeter, taking Q divided by delta T. So here's an example where we actually first have to calculate the specific heat of the calorimeter. So you are looking at the combustion of benzoic acid. We've got so many grams of benzoic acid with a heat of combustion of that value. We know how much water is in the calorimeter, and we know what the temp change of the water was. So we're going to use all this information to figure out how much energy went into the calorimeter. So Q of the reaction is equal to Q of the water plus Q of the calorimeter. In order to get Q of the reaction, I'm going to take M times delta H. So mass of benzoic acid times my delta H. The problem is I need this in moles and it's in grams, or vice versa. So I got to do one more conversion, get it into joules. Water, I'm using MC delta T. So that gives me 900 grams, specific heat, temp change, that gives me that value. I'm keeping a lot of digits here just to be safe. So with the Q of the calorimeter then, I can find it by subtracting the other two Q's. There's my Q. So then to get the specific heat of the calorimeter, I'm going to take the Q divided by the temperature change, gives me my specific heat of the calorimeter. Now, whenever I do a chemical reaction in this calorimeter, I know how much energy that calorimeter is going to absorb. So here's the second example, is if we already know the specific heat capacity of the calorimeter, we just want to know what the heat of combustion for this new material is. So different calorimeter. Would have made sense to use the original one, but pulled this sample or example from somewhere else. So now I want the delta H of the reaction. So the Q of the reaction, if you remember from 2 slides back, the Q of the reaction is equal to the specific heat of the calorimeter times the temp change. And then I'm going to simply divide by the moles of lactic acid, or in this case grams, then convert it into moles. So once you know the specific heat, it's pretty slick to be able to get the delta H for the reaction. Some kinds of specific heats, not specific heats, heat of reactions listed here. Notice that heat of reaction becomes heat of what reaction are you taking a look at? Heat of fusion, where we're taking melting an ice cube. Heat of neutralization, where we're taking an acid and a base and neutralizing it. So you have specific heat of reaction names that you're going to see in various problems. And then the last thing that I want to make sure that you all do is read section 5.8. I am not going to go through it. I think it's pretty straightforward. I don't think there's a need for me to talk about any of it. Occasionally something about burning of a fuel or burning of a food is going to appear on the AP exam. So just read through so you have an appreciation for what they are talking about. So that's the last video from the unit. You now have the ability to go do all the problems and get ready for that test.